Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video on optimization. So we did a bit of this last year and nothing has changed. Optimization is when you're finding a maximum or minimum value to a problem. Now we know that the maximum or minimum value of a function occurs when its first derivative is equal to 0. So the process is the same for all of these questions. Firstly, you need to find a function if you're not given one, then you differentiate it, then you find where the derivative is equal to 0, and finally you make sure that the point you have is a maximum or a minimum. Okay, let's apply all that to this example here. Rectangular prism holds 432 mils, square base, no top, and we're looking for the minimum surface area that it could have. Okay, so let's start by drawing in this case. So we have our rectangular prism here. The base we're told is a square. I'm going to label it side length x. So what we need to do is we need to write the surface area in terms of x. So to do that, we're going to need this dimension here. Now, I don't want to call this dimension here y or introduce another variable because we still haven't gone through differentiating functions that have more than one variable. We only know how to differentiate where there's one variable, usually x. That means I need to write this dimension here in terms of x. So the volume is 432 mils, which is the same as 432 centimeters cubed. So the volume of any prism, including rectangular prisms, is the area of the base times the height. So the area of the base times this height is equal to 432. That means that the height is just 432 divided by x squared. 432 divided by x squared is this dimension here. So now that I've written all of the dimensions in terms of x, in terms of one variable, I can write an expression for the surface area. So the total surface area, we've got the area of the base, which is x squared. Note that there's no square up here because it has no top. And then we find the area of the other four rectangles. So we've got 1, 2, 3, and one at the back of 4. All four of those rectangles have the same area. They have a width of x and a length of 432 over x squared. So their combined area, 4 lots of x times 432 on x squared. So we're just going to make that a little simpler. So 4 times 432 gives 1,728. And we have x over x squared, so that just can cross out one of the x's. This is our function. It is a lot of work, but once we've found the function, it becomes really easy. So your first step is always to find the function, and then we differentiate it. So the derivative of this, so the derivative of x squared is 2x. And then we're going to differentiate this. So this is 1728x to the power of minus 1. So then we move the minus 1, the power to the front, and we decrease the power by 1. So if I want to find where this is equal to 0, then I need to solve this equation. So we don't like dealing with fractions, particularly those with a variable on the bottom. So what I can do is I can times everything by x squared. Of course, 0 times x squared is just going to be 0. So 2x times x squared gives 2x cubed. 1728 over x squared. If I times by x squared, I get rid of the denominator. That's why I did this. I times this by x squared to get rid of the denominator. And then that just equals 0. So then solving this equation is simple because we have the x in only one spot. So we can add 1728 to both sides and then divide by 2. We get x cubed is equal to 864. So x is the cube root of 864. It's about 9.52. So if I substitute my answer here, about 9.52, cube root of 864, into my expression for the surface area, I get that the total surface area there is approximately 272 0.14 centimeters cubed. So note, when I'm substituting into this formula here, I don't want to round it to 9.52. I want to use the exact answer, which is the cube root of 864. That's what I substituted into here. Okay, so this is the process we're always going to follow. We come up with a function, which is sometimes difficult, then we differentiate it, and we find where the first derivative is equal to 0. Now, for this one, there was only one solution, so I don't really need to check whether it's a minimum or a maximum. All right, let's do one more optimization problem. So let's try this example here. Once again, it's going to be quite a bit of work to come up with the function, but I thought I'd give you another challenging one since we did this last year. All right, what is the maximum area a right-angled triangle could have if its hypotenuse is 12 centimeters? So let's start by drawing a triangle. We're told it's right-angled, and 12 centimeters is the hypotenuse. So to find the maximum area, I need a function for its area. I need like a equals blah, 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 then differentiate it. So we know that the area of a triangle is half the base times the height. The problem is I don't have a variable for either of these. See, if I call this x and I call this y, that's a problem because I don't know how to differentiate a function that has two variables, x and y. We haven't gone through that in class. But instead, what I can do is I'm going to use this angle here, theta. So using normal trigonometry, note that x is adjacent to that. I have cos of theta equals adjacent over hypotenuse. X is equal to 12 times cos theta. But similarly, sine of theta is equal to y over 12. So that means y is equal to 12 sine theta. So you're probably thinking, okay, what is this all about? Well, by writing this angle here, theta, I can write this side in terms of theta and this side in terms of theta. Now I have the base and perpendicular height. I have both of them written in terms of the same variable theta. Now I can come up with a function that only has one variable. So the area of this triangle is half times base times height. Of course, it doesn't matter which you call the base and which you call the perpendicular height. That is the area of this triangle. So I can simplify this a bit. Half times 12 is, of course, 72. It's 72 sine theta cos theta. That is an expression for the area of this triangle. So now I have an expression for the area. It's really simple. I just follow the same process. So I'm going to differentiate this and find where the derivative equals 0. So to differentiate this, I'm going to use the product rule. So I have my first function, 72 sine theta, and second function, I'll just use cos theta. So we'll go derivative of the first, so the derivative of sine theta is cos theta, so 72 cos theta, derivative of the first times the second, plus the first times the derivative of the second. So remember the derivative of cos is minus sine theta. So what I actually get here is 72 cos squared theta minus 72 sine squared theta. I need this thing here to equal 0. So hopefully you can see the only way that this can equal 0 is if this thing equals that. If 72 cos squared theta equals 72 sine squared theta. So really, what I want, because I'm only looking for acute angles here, I want sine theta to equal cos theta. If sine theta equals cos theta, then this thing here and this thing here will be equal and the derivative will be 0. So hopefully you know that this happens when theta is equal to pi on 4 radians or 45 degrees. Both of these equal the same thing. Sine pi on 4 or sine 45 degrees is 1 on root 2. Cos of pi on 4 is equal to 1 on root 2. So that means that the maximum area occurs when this angle here equals pi on 4 radians or 45 degrees. So if it equals 45 degrees, if theta equals 45 degrees, then x is equal to 12 cos 45, which is 12 on the square root of 2. And y will be the same. It'll be 12 times sine of 45 degrees, which is 12 on root 2. So the maximum possible area will be a half times 12 on root 2 times 12 sine 45 times cos, 12 cos 45. And so putting that on calculator, we actually just get 36. So 36 centimeters squared is the maximum area this triangle could have. All right, thank you so much for tuning into this video. This has been the luckiest maths teacher in the world. Have a great day.